x power negative 2 plus 1 is equal to negative 1. Negative 2 plus 1 is equal to negative. Then we have RE to infinity. Are we together? Eh? Okay. So we say that work done is equal to gravitational as mass of the S. And then we have this negative, which will be here. Then it's what? X or negative 1. Okay? So what do you say? So you say that work done is equal to gravitational potential. We say but negative mass of the S, or mass of the body times mass of the S. Then because x power negative 1 is equal to x power 1. So simply this is the work done required. Take a body from radius r to infinity. Negative g, mass of the body, mass of the S, over x power 1. Remember, intention deriving the formula 40 for escape velocity. But yes, we didn't substitute our limits first. Because we have limits. So this is negative, and then here we have what? 1 over x. 1 over x, here you have RE, and this is infinity. Okay? So if that the case, listen carefully on substitution of the units there. Negative g, mass, mass of the S. And then we say that the multiply is 1. What is this constant? Is 1. Then gravitational constant. So the value of x for this case is infinite. Minus 1 of what? 1 over, because what we are doing here, we are taking the value of infinity and substituting in x. And hence again we say minus 1, we take the value of our e substituting in x. Like that. So this is the square bracket. But by using a scientific calculator, for example, 9, let's say it's from 99. That's the end of the numbers. But when you say infinity, for example, if you have yes 1 exponent 100, and then so what's going to happen? I say that, for example, because we want to understand the infinity. Suppose the value of infinity is 9 exponent . So for example, 9 exponent 99. So if you find one over a very large number, now one is small, over what is very large number, the answer always is 0. So if that the case that now we say the work done, we are still discussing work done, we didn't start even the escape velocity. So we say that this is equal to negative g, mass of the body times mass of the s. And then here we have 1 over infinity, I told you it is 0, minus, then 1 over radius of the s, like this. Okay? So 0 minus that one's remain negative. Negative is negative, so the work done to take a body from the s. Notice this, you can be asked even these questions, because remember the work done to remove a body from the infinity to the distance r is negative, right? And the work done to take a body from distance r to infinity is positive, and it is true, because we say that work done, or however, the work done is in scalar quantity, because we use the dot product. So not this before, not this. So this is the formula of work done. So not these 2 points before I continue. The first point that he say the general formula of finding the work done to remove the body from what? From infinity to radius r or to RE is given as this formula. So the work done for that case is negative mass of the body, mass of the s, times universal gravitational constant over radius RE. So number 2, we say that the work done, the general formula, the work done required to remove the body from what? From r to infinity is given as what? Work done is equal to positive mass of the body times mass of the s times universal gravitational constant over the radius of the s. So take note of these 2 different formulas. So this one is from what? Which given by this one. So remove a body from r to infinity. So this one we say from what? Infinity to r, and this formula is from r to what? To infinity. So this is the radius of the s. So here from the infinity to the s surface, and with this formula we say that we remove the body from the s surface to infinity. Fantastic! That's the beautiful gravitation. You should have to be careful. You have to be careful, my dear student. So let us continue with our business of deriving the general formula that will help us to determine the escape velocity of a body. So we have been in 30 step or 4th step, okay, something like that. So I don't remember that which step, but let me call it the 50th step. So the 50th step, we say that because of our intentions, we are looking for the escape velocity. So the escape velocity, now we know about that one. So we say that at the 50th step, we say that the energy is always the gravitational energy, the gravitational energy is always conserved. Is always conserved. So what does it mean? We say that the work done required to remove a body from what? From the s surface to infinity. This will be equal to the kinetic energy of the body. Be careful. The work done required to remove a body from RE to infinity. This is equal to the kinetic energy of the body that is moving away from what? The s surface. So remember that the kinetic energy of any body at the s surface, or at the s surface, because we take consideration, we say that, yes, we say that at point A. It means that when point A on the S's surface, on the S's surface. So on the S's surface, we say that the work done required to remove the body from the S's surface to the infinity is equal to the kinetic energy that will be cause that body to move from the S's surface to infinity. So if that the case now, we say that the work done, we change it from the mass of the body times mass of the S times gravitational constant of an distance radius of the S. This is the work done, right? I've taught you how to derive this, the point where we are. So this one will be the work done, this work done provided to the body that required to move with the escape velocity is the one which is going to give the body the kinetic energy. And this kinetic energy from mechanics, fundamental mechanics, is mass, a half times mass of the body that moving away from the S's surface times its velocity. So square of its velocity. So this is velocity because now the body is moving from the S's surface to infinity where there is no disturbance or there is no any gravitational pulse. So this velocity now we call it escape velocity. Interesting. Don't confuse this kinetic energy, which I'm teaching you today on deriving the formula for escape velocity, and the gravitational kinetic energy. Gravitational kinetic energy, that's another story. And we determine by using the formula of centripetal force and and these also are force, the force of attractions between the body and and S. Don't confuse. Okay? So this is the kinetic energy that will cause the body to move from the S's surface to the infinity, where there's no gravitational pull. So if that the situation now, so we enjoy the beauty of physics like this, right? So then I'm very happy because I have taken you from far away to the beautiful concept of gravitation radius of the S like this. So then we say that we multiply by 2, and this one multiply by 2. So you have what escape velocity is equal to what? Twice mass of the S times gravitational or inverse gravitational constant of a radius of the S. Our intentions, we are deriving the general formula of escape velocity, right? So by deriving the general formula of escape velocity, this one we say that is equal to the square root of what? Twice mass of the S times universal gravitational constant of what? Radius of the S. So this is a general formula of escape velocity. So let me write it properly here with the HANA escape velocity, with its special HANA. The escape velocity, which is Vs, okay, Ve, not orbital velocity. This is given as the square root of twice times mass of the S times universal gravitational constant of what? Radius of the S. So this is a general formula that we need to remember for the rest of our life. Okay? If you didn't understand any point, please ask me in the comment sections, then I will help you, I will assist you so you can enjoy the beauty of what? Physics. Do you like physics? Do you like mechanics? Because you can like physics, but you say, I dislike mechanics. No, 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 no. This is the foundations of physics. So it's the fundamental, it's the foundations. Mechanics is the foundations of all other topics. If you master mechanics, none of the topic which will be critical for you. Okay. So then, so if that's the case, this is the first form of 40 of the formula of the escape velocity. So the sixth state, again, we can determine another form. We say that from the relationship between what? Between acceleration, gravity, and the what? And the universal gravitational constant. I told you, and we derived it together, that the products of mass of the S times the universal gravitational constant This is equal to acceleration due to the gravity times radius of the S square. But this is validly on the S surface. And this S and the escape velocity is computed on the S surface. Okay? Why? Because it's the minimum initial velocity required to remove a body completely from the act of gravitational pull. Okay. So if that's the case now, we say that if you recall the previous formula of escape velocity, we derived it and we found that it's the product of mass of the S times gravitational constant over radius of the S. So suppose that this is equation 1 and this is equation 2. So substitute equation 1 into equation 2. So we find that the escape velocity, general form of escape velocity, will be the square root of what? Acceleration gravity, radius of the S square of what? Twice. So this will be twice GR and S of what? RE. So again we find that the escape velocity is equal to the square root, so you simplify this. So the escape velocity is equal to twice times acceleration gravity, then times radius of the S. So determine the escape velocity, what do you need? You just need to know the value of acceleration due to the gravity, and the radius of the S. That's all. So it's a constant value. So you say that the escape, another formula for escape, the escape velocity, okay, the escape velocity can be found by this formula, which is twice G radius of the S. So this is a beautiful formula you have to remember for the rest of your life. Physics, advanced physics is full of the formulas, full of problem solving, full of closely related concepts. So you have to be careful. So those are the two formulas, and then now we can determine the what. For example, if you find a question that we say, let's say this is example. This is example, we solved the example 12. We did the example 12? Yes, 12, I think. So this is example, let's say 13, that given the value of acceleration gravity is 9.8 meter per second square, okay, and also will be given the radius of the S is equal to 6,400 kilometer, then determine the escape velocity. Very simple question. Escape velocity of 40 of the body. So you just need few steps. I think only 2 steps, and then you're done with these problems because it's very simple. So you thank God. In case you find a question like this one in the exam, you have to thank God first. It doesn't mean that if you find some other difficult question, you should not thank God. No, you have to thank God always. Okay, so the solutions, the first step, we just have to recall, you have to deduce, because I told you I don't claim the formulas. I can deduce this formula within 2 minutes, because I know where should I start and where should I end. But because I'm teaching, that's how am I going to step, right? So in case that you need to, because this is paper 1. According to the current syllabus, this gravitation is in paper 1. So you don't have enough time because you have a lot of questions within 3 hours. Okay, the first step we say that you have to recall. I recall because I told you how to derive. Recall the formula. The simplest formula, and the famous formula of 40 of escape velocity. Escape 40 velocity. So the formula states that the escape velocity is equal to the square root of twice G and what? Times 30 radius of the S. So escape velocity is equal to the square root of twice times 9.8 meter per second. So this is meter per second square times radius of the S, which is 64 exponent 3, and this is meter. So meter times meter is meter square. Then you have per second square. So if you find the square root, then you find that the unit will be meter per second. So just use your scientific calculator, do that simple computations quickly, and then let us go to other concept. So times what is 6,400 exponent 3. So then find the square root of it. So the escape velocity is 11,200 meter per second. This is equivalent to 11.2 kilometer per second. Fantastic. Can you compare it with orbital velocity? Orbital velocity, we deduced it as 3 kilometer per second. So the escape velocity is how many times compared to the 3 times? Almost it's more than 3 times or 40 of orbital velocity. So understand the concept that I'm speaking to you. So you say that the escape velocity of what? Of the body is 11,200 meter per second, or it is 11.2 kilometer per second. You are done. Okay, so then if that's the case, I want to show you, or I want to teach you how the questions of escape velocity have been asked in relation to the gravitational potential energy. Okay. Or I think that, no, so I think yes. That's a very important point. But again, in the homework, I ask you that to derive escape velocity, if you remember in one of the questions, that he determined the escape velocity. So from the homework 8, yes, I ask you again that to determine the escape velocity in other. So let us just formulate the formula, basic formula for you. Then I will leave the homework for you. Use the body escape from the above the Earth's surface as at a distance of that one, that is. Okay. So the questions, this is example 14. We say that derive the formula that determine the escape velocity of a body in any planet. Constant the escape velocity from the Earth's surface in any other planet. For instance, you'll be given some problems and determine the escape velocity in Mars, or in Jupiter, or in Neptune, or in Uranus, or in Saturn, or in, see? So how can you solve those problems? So this is the how. So we say this is simple, very simple. Say that solution. We may recall just the formula for the escape velocity on the Earth's surface. We say that this is twice mass of the Earth times 30 universal gravitational constant of 40 radius of the Earth. You remember that? So then, if that's the case, we say that now we have to say that in the escape velocity in other, so the escape velocity in any planet depends on what? Depends on universal gravitational constant, mass of that planet, and hence radius of that planet. What does it mean? We say that suppose this is the planet's surface. I want you to understand. So this is the body that you want to escape. So say that consider, so that the first step, so you go for the second step. The second step, we say that consider the figure below. So you say that suppose we have a planet surface here we have mass of the planet. This is the body of mass m, right? And then here we have radius of the planet. You have to understand, physics is not difficult. So this is the distance between those 2 points. Suppose this is point A, and then the intention of astronomer or maybe spacecraft specialist is to take maybe a body from certain planet, from Jupiter to a certain distance, which we call it B, right? So if that's the case now, we say that the distance between point A and the center, we call it x, right? And hence we say that suppose the small distance that we took this body is called the x, right? So similarly, you derive the work done required to take, and you'll find that it is mass of the body, there's mass of the planet, times 40 gravitational constant of a radius of 40 of the planet. And thus, you know, the kinetic energy of the body is equal to a half mass escape velocity in any other planets, let's say, square. So this is question 1 and question 2. So energy is conserved, right? So if energy is conserved, we say that the third step, we say that energy is conserved, right? Energy is conserved. So if it's conserved, we say that work done is equal to kinetic energy gained by the body. So the work done is equal to mass times mass of the planet, gravitational constant of a radius of the planet is equal to a half mass of the body times 40 escape velocity of 40 in any other planet. So if you derive the final formula, velocity, escape velocity at a particular planet will be what? Will be twice mass of the planet times gravitational constant of a radius of the planet. Let me write it clear. Then leave the homework and end this lecture and join me in the lecture 10 of problem solving gravitation. So we say that velocity of the planet is equal to what? Is equal to square root of what? Twice mass of the planet times gravitational constant. Then velocity of a radius of the planet. So that's the general formula. So now let me leave the homework, simple homework, and this is homework 9. We say that given the inverse of gravitational constant G, inverse of gravitational constant G, 6.67, from negative 11 Newton per kilogram square, and then we say that per kilogram square, so gravitational constant, and then Newton per kilograms meter square. So meter square. Okay? So meter square. Then you are given sort mass of the S. I taught you how to derive it. It is 6 exponent 24 kilogram. And also you are given radius of the S is equal to 6,400 kilometer. Then determine the escape velocity of the body from the S's surface. The escape velocity from the body. Okay, the escape velocity of what? The escape velocity of the body. So that's the question. Very simple question compared to other homeworks that I have left it for you. I left it to you. So this is, we say, half twice mass of the S is 6 exponent 24 n times G everything is clear. Okay, so if that's the case now, this is the end of sessions or lecture or period 9. I would like to thank God who have prepared me and also here have enabled me to prepare all of these materials. And I also thank God who have taught me how to teach it, because this is God's grace. And I'd like also to thank you for taking your times on watching this video. In case that you didn't subscribe, make sure to subscribe so that you can get notifications in case we add any new video. And I would like also to invite you in the lecture or period or session 10 of problem solving on gravitations, especially all about the gravitational energy. So thank you very much. May God bless you. And I would like to pray for you and pray for me. And let us meet in the next lecture of problem solving, when we'll be enjoying now the computations in mechanics. So see you in the next lecture. This is Olenjolaim.